Minimization of nitrogen oxides from fossil fuel power plants using swarm intelligence technique. Abstract the pollutant from the fossil fuel plant threatening the entire world and ensure that the amount of emissions such as sulfur dioxide, SO2, and nitrogen oxides, NOx, must be reduced. Hence it is necessary that the emission constraint must include in the economic dispatch problem, and its objective is to minimize production cost with lowest emission. In this paper, swarm intelligence technique has been proposed to solve an emission-constrained economic dispatch problem. The performance of the proposed algorithm is tested on 6 unit test systems with various load demand and emission coefficients. The comparison of the simulation results prove that the proposed algorithm have a better performance than existing algorithms. Keywords: sulfur minimization, nitrogen minimization, emission dispatch, environmental dispatch, swarm intelligence. 1. Introduction. Due to the Strict Environment Act, the power industries must reduce the emissions from the fossil fuel power plants. The pollutant from the fossil fuel plant threatening the entire world, and ensure that the amount of emissions such as sulfur dioxide, SO2, and nitrogen oxides, NOx, must be reduced. Hence it is necessary that the emission constraint must combine with economic dispatch problem, and its objective is to minimize production cost with lowest emission 1 to 4. The mathematical approaches like interactive search, IS, approach, Newton, Raphson, NR, method, non-linear programming, NLP, and quadratic programming, QP, have been applied to solve economic emission dispatch 5 to 9. The classical methods may have difficulties in finding an optimal solution due to the longest execution time and presence of non-linear and discontinuity in the problem. The variety of artificial intelligence techniques and their hybrid versions has been applied to solve environmental emission dispatch problems 10 to 18. Based on the shallow water theory named water evaporation optimization algorithm, 19 have been applied to solve environmental economic dispatch problems. Recently, inspired by the foraging behavior of honeybees, researchers have developed artificial bee colony, ABC, algorithm for solving various optimization problems 20. ABC is a relatively new population-based bio-inspired approach with the desirable characteristics such as robust and easy to implement. Further, ABC does not use any gradient-based information, and it incorporates a flexible and well-balanced mechanism to adapt to the global and local exploration abilities within a short computation time. This makes the algorithm efficient in handling large and complex search spaces. In this paper, an ABC algorithm is proposed to determine the optimal solution for environmental economic dispatch problem. 2. Problem formulation. The reduction emission from fossil fuel-fired power plants is essential for power industries due to Clean Air Act amendments of 1990, and the problem can be formulated as: the total emission of generation EI can be 2.1 IIIIIPPE plus equals 2. EI is the function of emissions in kg/h, and AI, SSI and .I are the coefficient of emission characteristics specific to each production unit. 3. Swarm intelligence technique. The foraging bees are classified into 3 categories: employed bees, onlookers, and scout bees. All bees that are currently exploiting a food source are known as employed. The employed bees exploit the food source, and they carry the information about food source back to the hive and share this information with onlooker bees. Onlookers bees are waiting in the hive for the information to be shared by the employed bees about their discovered food sources, and scouts bees will always be searching for new food sources near the hive. Employed bees share information about food sources by dancing in the designated dance area inside the hive. The nature of dance is proportional to the nectar content of food source just exploited by the dancing bee. Onlooker bees watch the dance and choose a food source according to the probability proportional to the quality of that food source. Therefore, good food sources attract more onlooker bees compared to bad ones. Whenever a food source is exploited fully, all the employed bees associated with it abandon the food source, and become scout. Scout bees can be visualized as performing the job of exploration, whereas employed and onlooker bees can be visualized as performing the job of exploitation. In the SI algorithm, each food source is a possible solution for the problem under consideration, and the nectar amount of a food source represents the quality of the solution represented by the fitness value. The number of food sources is same as the number of employed bees, and there is exactly one employed bee for every food source. This algorithm starts by associating all employed bees with randomly generated food sources, solution. In each iteration, every employed bee determines a food source in the neighborhood of its current food source and evaluates its nectar amount, fitness. The ith food source position is represented as she, where I equals 1, 2, n is a d-dimensional vector. The nectar amount of the food source located at she is calculated by using the EQ, 7. After watching the dancing of employed bees, an onlooker bee goes to the region of food source at she by the probability pi defined in EQ, 8. Where n are randomly chosen indexes. Although k is determined randomly, it has to be different from I. Is a random number between -1, 1. If its new fitness value is better than the best fitness value achieved so far, then the bee moves to this new food source abandoning the old one, otherwise it remains in its old food source. When all employed bees have finished this process, they share the fitness information with the onlookers, each of which selects a food source according to probability given in EQ, 8. With this scheme, good food sources will get more onlookers than the bad ones. Each bee will search for better food source around neighborhood patch for a certain number of cycles, limit, and if the fitness value will not improve, then that bee becomes scout bee. NK, 2,1. DJ, 2,1. IJ. It is clear from the above explanation that there are three control parameters used in the basic SI, the number of the food sources, which is equal to the number of employed or onlooker bees, n, the value of limit, and the maximum cycle number, MCN. Parameter tuning, in meta-heuristic optimization algorithms, influences the performance of the algorithm significantly. Divergence, becoming trapped in local extrema, and time consumption are such consequences of setting the parameters improperly. The SI algorithm, as an advantage, has few controlled parameters. Since initializing a population randomly with a feasible region is sometimes cumbersome, the SI algorithm does not depend on the initial population to be in a feasible region. Instead, its performance directs the population to the feasible region sufficiently. 4. Swarm intelligence technique for environment economic dispatch. The proposed algorithm for solving EED problem is summarized as follows. Step 1, read the system data. Step 2, initialize the control parameters of the algorithm. Step 3, an initial population of n solution is generated for each solution she, I equals 1, 2. N, is represented by a d-dimensional vector. Step 4, evaluate the fitness value of each individual in the colony. Step 5, produce neighbor solutions for the employed bees and evaluate them. Step 6, apply the selection process. Step 7, if all onlooker bees are distributed, go to step 10. Otherwise, go to the next step. Step 8, calculate the probability values pi for the solutions she. Step 9, produce neighbor solutions for the selected onlooker bee, depending on the pi value, and evaluate them. Step 10, determine the abandoned solution for the scout bees, if it exists, and replace it with a completely new randomly generated solution and evaluate them. Step 11, memorize the best solution attained so far. Step 12, stop the process if the termination criteria is satisfied. Otherwise, go to step 3. 5. Simulation results and discussion. Software package implementing the new proposed technique is developed using Intel R Core TM 2 Duo CPU 2.10 GHz processor. To illustrate the validity and effectiveness of the proposed technique, the 6 generating units test system given in 19 is studied and solved. The control parameters of SI algorithm are chosen as colony size 100, maximum cycle/generation number, MCN, 100, and limit value 30. In order to show the effectiveness of the proposed ABC algorithm, it has been tested on 6 generating unit system for the load demand of 700 MW, 800 MW, 900 MW, 1000 MW. The system particulars are available in the literature 19. The simulation results obtained by the proposed as well as existing algorithms are presented in Table 5.1 and 5.2. The results shows that the proposed ABC algorithm achieves the minimized emission of NOx for all load demands than existing algorithms. For the load demand of 700 MW, the proposed algorithm reaches the minimized emission value of 434.09 kg/h. For 800 MW the emission value is 548.54 kg/h, for the load demand of 900 MW it attain the value of 682.45 kg/h, and for the final load demand of 1000 MW it obtain the better value of 837.45 kg/h. In all cases the proposed ABC algorithm achieves the competitive results with fully satisfies the system and problem constraints. The total production cost obtained by the proposed algorithm is also compared with existing techniques is also presented in Table 5.1. The comparison also shows that feasibility of the proposed algorithm reach better results in terms of least production cost. The proposed algorithm have capability of online implementation for reduction of emission and production cost. From the comparison it is clear that ABC algorithm outperforms the existing algorithms. 6. Conclusion. The emission-constrained economic load dispatch, excelled, problem is a sub-problem of an optimal power dispatch. In this paper, emission-constrained economic load dispatch problem is solved by using swarm intelligence technique named artificial bee colony algorithm. The simulation result of the proposed algorithm is compared with existing techniques. From the comparison it is clear that the proposed algorithm obtain the better results than existing algorithms for the load demands of 700 MW, 800 MW, 900 MW, 1000 MW. In all cases the proposed algorithm clearly satisfies the system and problem constraints. The simulation results shows that the proposed algorithm have the ability to online implementation.